Multi-threaded custom processor by Team Sunkara Manoj, Sachin Subramanya, and by Liang. Similar to the instruction memory used in a single core processor, the instruction memory here also has the ability to accept instructions from an external interface. While we are writing the data into the instruction, there is a new mode called debug mode is created. When the system is in the debug mode, an OOP is injected into the pipeline to make sure there are no dependency issues because of instructions coming out while they're being written into the instruction memory. A similar register file is also used. However, in this case, we are using a 128 by 64-bit register file instead of the 32 location 64-bit register file that was used for single core. The 128 cores, the upper 2 bits are used to identify the registers for each bit. So all the registers from 0 to 31 with the upper 2 bits of 0 are the 32 registers allocated to thread 0, and the upper 2 bits of 0, 1 are allocated to thread 1, and so on. Each thread gets 31 registers and one special purpose register which is grounded. The data memory also has the capability of accepting data from an external interface while in debug mode. While in debug mode, as we are already passing no ops from the instruction, there is no problem with the data dependencies. So when in debug mode, we can write the whatever values we want into the data memory. When we are not in the debug mode, the instruction memory acts as a normal data memory and the code works. A simple thread scheduler is used. This is achieved by instantiating a 2-bit counter that counts from 0 through 3 and then goes back to 0. So if we look at this, as the time progresses, initially the thread 0 is executed, then thread 1, then thread 2, and then thread 3, and this just repeats. So this is a simple thread scheduling mechanism that we used. So we have 4 program counters and a mux user, and then we select each program according to the threads scheduler. So like the scheduling operation explained earlier, initial first thread 0's addresses goes in, then thread 1, thread 2, and so on. To identify the instruction, the thread of the instruction, the thread is also sent along with the instruction throughout the pipeline. And the register files. So instruction is still 30. The instruction is still 32-bit instructions, and it has 5 bits of data. To differentiate the registers of the threads, we concatenate the first 2 bits of the address with the corresponding thread and the instruction address, and then send it to the register file. It is a single register file interface that is with 2 BRAMs. However, they are segmented internally into 4 different blocks. And once the threads travel through the registers and reach the EX stage, and jump and branch addresses are calculated, their corresponding thread value is also sent back. So the corresponding program counter only jumps. That is, if the jump is issued by thread 0, program counter 0 only jumps, while like 2, 3, and 4 doesn't. And also to make sure that we are writing back into a proper register and to enable the register isolation, the thread value is also sent through the write back stage and is concatenated with the RD to write back into the register file. Here we see the register file organization. So with initial 2 bits as 00, we have 32, and then with 01 we have 32, and so on. That makes a total of 128 registers. Now looking at the simulation of the project, a simple bubble sort that sorts 6 digits was used, and each thread actually tries to sort the values at a different location. So thread 0 tries to sort 6 values starting from 0 and ending at 5. Thread 1 does the same for addresses 10 to 15. Thread 2 does the same for 20 to 25, and thread 3 does the same from 30 to 35. So here we are initially writing these data values using the debug mode into the data memory. As you can see, we are writing 503.210, 503.210 into the corresponding addresses. And individual thread bands are calculated, and the final processor is only done when all of them are done. This is to ensure that We don't assume that our process is done while one of the threads is still running. As you can see here, the done process only goes high when all the 4 threads are done. Now to verify our bubble sort program has worked, we have also used this debug mode to read from the data memory to ensure that we get the proper values. So as we can see, the data has been swapped. Now we wrote 543210, but now we can see that the data has been swapped to 012345. And this has been done by all 4 threads. Now let us look at the deployment of the core on the FPGA. So an automated script was written to configure the FPGAs and then do the initial CPCI programming as well as the RKD building. After that is achieved, we want to write the bit file into this. The binary was generated and then a script was written to program our register. This script is the same script used for a single threaded code which has an instruction write, data write, and run functions in it. After the instructions and the data has been written, let's take a look at the data before we run. As we can see, data 0 through 5 have the addresses 0 through 5 has the value of 6, 5, 4, 3, 2, and 1. Similarly, addresses A to F, that is 10 to 15, also have 6, 5, 4, 3, 2, 1. Also 14 through 19, that is decimal values of 20 to 25, also have 6 to 1. And finally 1E to 2, 3, that is 30 to 35, also have the values 6, 5, 4, 3, 2, 1. Now let's run the program and see. As you can see in data 0 to 5, the addresses have been sorted into from a descending order into an ascending order. 'Similarly, the data stored from addresses 10 to 15 have also been sorted. '20 to 25 also have been sorted. And finally 30 to 35 also have been sorted. So this proves that our multi-threaded processor works. We aim on deploying this multi-threaded processor to develop our own custom network processor in the future. Thank you.